Welcome to Otherwise. I am your host, meteorologist Nathan Scott. Today I'm going to switch things up a little bit. Instead of talking just about meteorology, we're talking about other earth sciences, geology. And joining me right now is Scott Alsbrooks with the State Office Geologist Department. Scott, earthquakes in Arkansas, something we normally don't talk about, but they do happen here, and we've had significant history when you look back to the 1800s. First of all, let's talk about what is an earthquake? Why does an earthquake develop in the first place?
An earthquake is a release of energy, seismic energy. Typically, it occurs along a fault that separates two blocks of rock, and when they move in opposite directions relative to each other, that sudden release of energy is what we feel is an earthquake.
And we have something from your website here from the Office of State Geologists. We just want to pull that up. There are different types of earthquakes. And you can just take this full if you can, Michael. So we have strike-slip fault lines, dip-slip faults. That sounds quite confusing to somebody that has no clue about earth science. So break that down for us simply as possible.
Sure. It's relative to the movement. As you can see, a strike slip is one side of the fault is moving horizontal to the other side of the fault. A normal fault or reverse fault, which are the two different types of dip slip faults, one is moving up relative to the other side. That's where you get a hanging wall, foot wall type relationship. And you can see by the models there how they're moving. And when this movement occurs, that point of movement rupture is what we call the focus. And that energy travels out, and once it intercepts the surface, it becomes the epicenter, known as the epicenter. When you hear the epicenter of the earthquake, it's the point directly above the focus where the earthquake originated, where the rupture started. And so, given the length of the fault will tell you how big the earthquake's going to get. In other words, the more rock that moves, the longer that fault is that ruptures, the larger your earthquake will be, and the longer lasting that earthquake will be as well.
When we talk about earthquakes, we think of California. We think of the Pacific Northwest, Oregon, Washington. Not so much here into Arkansas, but there's significant history because we have a fault line that you probably have learned as a kid, and it seems like it's sleepy at times, but then it awakens other times. What is this fault line, and why is it so important to monitor it all the time?
Well, that's a great series of questions. We'll start out west. California and the Washington, Oregon, they're on what we call the Pacific Plate boundary. They're on a plate boundary. So as those plates shift and move, it's where they get the earthquakes and the reason. San Andreas Fault is a great example of that. And so it's a strike slip. That movement's horizontal, gets earthquakes. And 95% of the world's earthquakes occur along those plate boundaries.
Yeah, we have a map of the world, courtesy from the USGS. And it shows just in the past day, all these dots that you see are earthquakes that have been happening across the world.
And you can see most of them are around these red lines, which represent the plate boundaries. However, you can see in the central part of this plate, the North American plate, we've had some earthquakes. And 5% of the earthquakes can occur within in the plates, and we call those intraplate earthquakes. And New Madrid is a great example of one, and that's the fault zone that's up in the northeast corner of our state. It extends from Marktree up to Blyville and then on up into through Missouri and Illinois. And it's made up of three segments, and it represents a time in the past when the earth actually tried to, the ocean tried to pull apart, the crust tried to pull apart it there. It's a failed rift. There's a great one that's going on right now is over in the Eastern Rift Valley in Africa, where Ethiopia, and it's actually spreading. And this was one of those places where it failed, and then subsequently got covered up over time with the Mississippi River and the deposits and stuff. But deep down, those faults still are there. And occasionally, with the movement of the plates and stuff, you get a little bit of transference of energy into those faults, and they get released as earthquakes. And you were talking about the large ones back from the 1811 and 1812 series.
And these plates are always moving.
Correct.
But this one, specifically over northeast Arkansas, the boot heel of Missouri, the new Madrid, is concerning for us because it did produce something wild back in the 1800s. Let's talk about the history of the new Madrid fault.
Sure. And as I said, these are intraplate faults. You're in the middle of a plate, which you wouldn't expect to have large earthquakes. But with their geologic history in the past, Again, it's a weak zone, and these faults exist. And so as the North American plate is being pushed or pulled, if you will, or being pulled as the ocean is in the Atlantic is spreading, and we're getting further away from Europe and Africa, and as we're crashing into the Pacific plate, which is giving us earthquakes out there, some of that energy is transferred into the middle of the plate, and it accumulates on these weak zones, these faults in the central part of these interplate faults. And then occasionally you have a release of that energy, and that's what New Madrid was. And historically, we had a series of earthquakes in 1811, started, I believe it was December 16, 1811. We had the arm that extends into Arkansas ruptured first. And estimates was it was around a magnitude 7+ earthquake.
Which is huge.
Yeah, it's a big earthquake.
I mean,
it's a major earthquake.
We think about the 1989 earthquake that hit San Francisco.
Loma Prieta. Mm-hmm.
What was that one?
That was, I believe, a 7.4, 7.6. So it was a large earthquake.
Yeah.
And then there was it was very similar in magnitude as one of the larger earthquakes, the San Francisco earthquake. Mm-hmm. I believe it was probably closer. It was around a 7.6 in 1906. So that's the size earthquakes that we had. Now, what's kind of unique about an intraplate setting is sometimes you have different segments of these faults. And so that first segment ruptured, and then a second segment, which was the segment that went from the Boot Hill, Missouri up into Illinois, it ruptured in January. So a few weeks later, you had a second major, just as big, if not bigger, earthquake.
Wow.
And then it was followed up in February. So within a 3-month period, you had one that was even larger, because it was that central fault that stepped over that connects the two faults. And that fault has a upward movement. And so when it ruptured, it actually ruptured, and that's where you get those historical accounts of the Mississippi River running backwards, the waterfalls on the Mississippi River, and that was because of the geometry of that fault. It ruptured enough up and translated up to the surface to raise the ground, and basically where it crossed the Mississippi River, causing.
Can't even imagine that. And I heard that earthquake was so strong it rang church bells in Charleston, South Carolina.
That's correct.
That's just wild to think of.
And I think it has to do a lot too. We can talk about the geology and how the rocks in the eastern U.S. are much more efficient at transmitting seismic energy versus the rocks out west. Rocks out west are warmer, they're more broken up, and they're a lot younger. So they do not transmit that seismic energy as efficiently as you see with in the eastern U.S. And this is a great example of that.
Yeah.
Where similar magnitude earthquakes, the magnitude 5.8 in Virginia and a 6.0 in California, it's barely felt out of the state of California. When you can see it's felt as far east as even the Mississippi River or Arkansas with a similar magnitude earthquake. And it just has to do with these rocks being much older, colder, more continuous, dense, and it's just they're much more efficient transmitting that seismic energy. So that's something that for your viewers to keep in mind is even a smaller earthquake here can have more profound effects than a similar size earthquake out west because of this geology.
I went through that one, and I'm going to talk about my experience going through the earthquake, but we got to take a short break.
Sure.
We're going to be back with more Weatherwise and geologist Scott Alsbrooks with more on the earthquakes here in Arkansas and the New Madrid fault line coming up. Welcome back to Weatherwise. I'm meteorologist Nathan Scott. I have geologist Scott Alsbrooks joining me talking about earthquakes here in Arkansas. And we were finishing up before we went to break talking about the earthquake that hit Mineral, Virginia back in August of 2011. I actually felt this because I was in Maryland, and I will never forget that day because I was at a pizza restaurant waiting in line, and then all of a sudden I felt this shaking. And next thing I know, it felt like you were in a fun house.
Yeah.
It didn't last very long,
right?
But you could hear the building move. It was very unsettling. I don't want to experience that ever again in my life. I don't know if you've ever experienced an earthquake. It's definitely unsettling.
I've experienced several of them, including a couple of magnitude 4.5, 4.7s in central Arkansas. It is very unsettling. In fact, the one I experienced, you could hear the rumble come. and then you felt the wave come through you and pass through you, and it's kind of like you said, you just kind of felt that
I felt the floor go. Yeah,
that's right.
I felt a wave go through.
That's right, and that's a great point is the waves that you feel. When the earthquake happens, you've got a P wave, which is that initial shock wave that races out, followed by the shear waves, and then the surface waves is what you were feeling there at the end with the rolling, and that's your Love and Raleigh waves, and those are the ones that cause the most damage and stuff to structures and bridges and such.
Yeah, being a part of that experience, you looked at other customers and you had this nonverbal communication because no one knew what was happening.
Right.
We'd never experienced an earthquake like that in Maryland before. And it was like, is this what it really feels like? And I'm just like, do I get under something? How long is this going to last? I mean, it freaked me out.
Yeah, and that's the thing. An earthquake is a non-notice event. And I mean, it gives you very little, if no warning at all. And it happens, and you don't have a lot of time to react. I mean, the first thing you want to do is not panic. And the second thing is to, if you can, like if you've got a place that you can get under a sturdy table or a bench or desk or whatever it is, piece of furniture that can kind of could protect you from anything coming from below. Because that's one of the biggest factors in injuries and deaths and earthquakes is stuff falling on people. And so we always encourage folks to review their safety precautions, to look at their surroundings. If something happens, where am I going to go? What am I going to do? Just case the situation. It's very similar with the weather and severe weather. Kind of know where you're at, be aware, and what I do in a given situation.
So this is a serious thing we need to think about. Just like we do tornado drills here in Arkansas, because tornadoes are very common, we need to start incorporating earthquake drills, and just in case something happens, because when we look at this map, this is very significant. And break this down, because I'm seeing red right along the Mississippi River, Arkansas, Tennessee. I'm thinking that's where I don't want to be if the new Madrid really starts to go. Meanwhile, it does diminish here in Little Rock, but still we would feel the effects.
It's basically, this map it's the USGS hazard map, and it's showing the likelihood of it's called percentage of gravity of what you would expect the amount of shaking. And so you'll have a higher probability of having a certain level of shaking in Northeast Arkansas, because that's where you have New Madrid. In fact, that's outlining that arm that extends into Arkansas. So in Northeast Arkansas, you definitely want to have your awareness and earthquake plan and what you're going to do in the event of a large earthquake. We're going to feel it here. We're going to know it. I think in certain areas of the city of Little Rock, it's going to be more pronounced because of the underlying geology, as we talked about a little bit ago. In the east part of the city, you've got unconsolidated material, soil, clay, silt, sand. It's going to behave a little bit different. It's may enhance the shaking versus in the West Little Rock, where you're built upon the rock and stuff. It may not be significantly different, but I think there'll be some places you will know. But regardless, whether you have a large earthquake here or not, you're going to know it. And then also for us, we have to think about the secondary effects, maybe the loss of power, ruptured natural gas lines, things like that, transportation and stuff. So even though we may not have the same kind of hazard, a large fault lying under Little Rock, this will be a regional, if not a nationwide impact if this was to happen again, as it did in 1811, 1800.
But Memphis is probably the place you don't want to be. We would see significant failure of infrastructure in Memphis.
There's always that possibility. Now, give you a good example, the AutoZone headquarters there has done retrofitting. They have isolation ball bearings under their building. So there's been a lot of work in that area on the same way with the I-40 bridge over the Mississippi River. The RDOT, yes, RDOT and the Tennessee Department of Transportation have worked together. And so there's been some retrofitting, there's been some awareness over time, and so things are that. But again, anywhere you have unreinforced masonry building, anywhere you have lots of tall buildings with lots of glass, those are the areas you don't want to be. And that's why we always encourage people, if an earthquake happens, do not run out the building. Stay where you're at. Try to find a suitable place to protect yourself, protect your head in case for falling debris, but do not run outside, because that is where the most hazards are going to come from the shaking and the glass falling and stuff. And so when you were there in Maryland, you stayed where you were at. You didn't.
I mean, I thought about going outside, but it happened so quick. It's like
Right.
you didn't really have time. It probably lasted, it felt like minutes, but
Sure.
it was only like probably 10, 20 seconds.
Right. But you did the best thing is at least staying where you're at and not running out, because that's where you run into the problem. There was a earthquake. It was a I believe it was like a 5.8, 5.4 up in Illinois back in 2008. And there was brick facades falling off buildings and stuff, and you could see in the front where the damage was. And so we just recommend don't do that.
So as a geologist, are you expecting the new Madrid seismic zone to be active in your lifetime, in our lifetime?
Well, it is active. I mean, we have our
Could it produce another 1811?
Statistically and based on the geologic record, based on historical record, at some point we expect it to have another magnitude 7+ earthquake on it. The USGS gives a probability of about a 7 to 10% chance in the next 50 years. Or any 50-year period of having a magnitude 7 earthquake. I don't want people to worry. I want people to just be aware, and then with that awareness, that preparation comes. Like, okay, what am I going to do? Where am I going to be? What I need to do? I mean, we in this state, up in that area, don't have, as you said, like Memphis, where you have more unreinforced masonry buildings, you have more infrastructure, you have more potential for things to happen, people to get injured. We're more rural in that area, but still, we need to prepare. People need to do their plans. So I don't want to overhype or worry people, but at the same time, I want to encourage people to be aware of what's going on. And it's like all hazards. Have a plan.
I think the most concerning thing is because it comes without warning. Like,
yes,
whether you have watches, you have warnings to let you know, hey, something's going to happen. Earthquakes, you don't have much notice. I mean, you're not going to have something pop on your phone to say, earthquake in 1 minute.
That's right.
It just happens.
And it's there are some early warning systems out there. In the West Coast, the USGS Shake Alert has developed an early warning system for California, Washington, and it's a regional system. There's other countries, Taiwan, Japan, that have national systems. It takes a very dense network to set up something like this, because once it triggers, it basically how many of the stations the P wave gets to initiates it. And so it tries to do a quick estimate and get the word out. Well, this is a moderate earthquake, or this is a large earthquake, or, know it's coming. And so you have kind of the issue with false positives. Sometimes they can trigger. I think over time, as technology does, it gets better and better, and the ability to get better. And maybe someday we'll see one here, because we have a pretty dense network in the state, and especially up in the New Madrid area. To me, the biggest benefit of an early warning system is it's for the critical infrastructure, your nuclear power plants, your trains and stuff. Those are things that you would want to immediately start to shut down if there was a significant earthquake. And so I can hopefully foresee in my lifetime that system gets better and more employed in areas where you have potential of seismicity, especially large earthquakes.
Sure. Well, Scott, we are out of time. I mean, you have said so much great information. We're going to have you back on just to talk about the geology of Arkansas alone, because it's such a unique place to live in. We've got minerals here. I want to discuss about that in the future, and other stuff like, hey, why does Pinnacle Mountain look like a volcano? We'll talk about that coming up in future episodes. But Scott, thank you again for joining us here on Weatherwise. We'll be back with more after this. Last week when it was barely cold, I went outside and I checked out the snowflakes that were flying around. They were just a little flurry activity for the most part, but those were some intricate snowflakes that were landing on my jacket and on the ground. And I got my camera out and I took some pictures of the snowflakes. And this is what I got just from my camera alone. But you have that classic six-sided, intricate design of a snowflake. That's known as a dendrite. And this is pretty close. This is the fiber from the coat that I was wearing. So some snowflakes look like this. Other snowflakes look entirely different. Let's talk about the growth of a snowflake. First of all, you have what's in the cloud. Of course, you have water droplets. But how does a water droplet form to begin with? And that is due to little particles in the air, dust particles, or maybe it's a pollen particle. Those are always floating around. And when you have a cloud that is really cold with a temperature, you have super cool water droplets, or water droplets that still exist in the liquid phase, even though the temperature is 32 or well below that. That will stay a liquid water droplet until it encounters one of these particles floating around, and then it freezes directly onto that particle. And in this case, we have a hexagonal plate ice crystal that forms. As this plate is making its way through the cloud, getting closer and closer to the ground, it will run into other hexagonal ice crystals, and those will merge or coalesce into one ice crystal. Along with that, as it's going through different temperatures of the cloud and also the moisture amount in the cloud, you will get these branches. As the gas phase of the cloud goes into solid phase, ice crystal phase. This is known as deposition. So you go from water vapor directly to ice crystals forming these little branches. And no snowflake is alike. That's just because every snowflake takes a different path of what kind of humidity it goes through and what the temperature is. So you get an infinite amount of possibilities. That's the growth of a snowflake. Now let's break it down to types of snowflakes. You may have not noticed this before, but next time it snows, go outside and see if you can take a picture and see these different types of snowflakes. We have thin plates, needles, hollow columns, stellar plates, and the beautiful dendrites. And it all is determined by the temperature in the cloud. So we get thin plates when it's 25 to 32 degrees Fahrenheit. When it's 21 to 25 degrees Fahrenheit, you get needles. Then when it's 14 to 21 degrees, it's hollow columns, 10 to 14, stellar plates, and then dendrites happen about 3 to 10 degrees. Let's go over to Storm Track 11 now, because this is a great website that is done by a physics professor out of Caltech who has taken microscopic pictures of snowflakes. And there you see we've got stellar dendrites, the really intricate designs, columns and needles, cap columns, fern-like stellar dendrites, triangular crystals, which I never knew existed, and then sometimes, on rare occasion, you will have the beautiful six-sided regular dendrite merge with another dendrite, and you can get 12-branch snowflakes. Also, when you have a snowflake that goes through a column of air with super cool water droplets, those water droplets would freeze on contact with the ice crystal and produce that fuzzy look right there that you see. And this is known as grapple. And it's known as also soft hail. We get grapple here sometimes. Those are the Dippin' Dots type of snow that you see sometimes. So that's a really cool website. It's snowcrystals.com if you're interested. Now we're getting out of winter weather. We'll be going into, of course, spring, and we'll be talking about more severe weather, lightning, flash flooding. All of that will be coming up in future WeatherWise episodes. Thanks for watching. Make sure, if you have any questions, send your questions to my email or my Facebook. My email, of course, is nscott@thv11.com. Have a great day, and I'll see you soon.